Section A, Molarity.
Capital M stands for molarity. The molarity of a solution is the number of moles of solute in 1 liter of solution, so it would be like the moles of a silly putty in a solution of water. We measure molarity in moles per liter, so if we say we have a 2-molar solution of sodium chloride in water, we mean there are 2 moles of sodium chloride per liter of solution. The equation you'll use to find the molarity is N, the moles of solute, that's the lesser or solid part of a solution, divided by V, the volume of solution in liters. And this is handy. You can use the volume and molarity of a solution to find the number of moles of solute you have by rearranging the molarity equation to read N, the number of moles, equals molarity, capital M, times V, the volume.
We're going to show you a typical molarity calculation. We'll take a lot of information we need for the calculation from the balanced chemical equation that represents the reaction NaOH sub AQ, which is aqueous sodium hydroxide, plus HCl sub AQ, which is aqueous hydrochloric acid, yields NaCl sub AQ, which is aqueous sodium chloride, plus H2O, water. The term aqueous, represented by the subscript AQ in the equation, just means your solution has water as the solvent.
The balanced equation not only shows which chemicals are reacting to form what product, it also shows what ratio of reactants, or starting stuff, you need for the reaction to go off with no reactants left unused. According to the balanced chemical equation, NaOH and HCl react in a 1-to-1 ratio to form water and sodium chloride. So for each mole of HCl we use, we need 1 mole of NaOH.
So here's the question. How many milliliters of a 0.400 molar solution of sodium hydroxide do we need to react with 0.500 liters of 0.200 molar hydrochloric acid? To figure it out, we'll use the molarity equations we just talked about and a new variation to find volume. Volume equals the number of moles divided by the molarity.
Like we said, the balanced equation dictates that the number of moles of HCl we have will equal the number of moles of NaOH. So let's find out how many moles of HCl we're starting with in our 0.500 liter sample. To find out how many moles of HCl we have, this is the equation we need. N, the number of moles, equals the molarity, M, times the volume, V. Easy enough. Our molarity is 0.200 moles per liter. Multiply 0.200 moles per liter by the volume of HCl, 0.500 liters, and we get 0.100 moles. That's how many moles of HCl are in the 0.500 liter sample.
Although we don't have enough information to calculate how many moles of NaOH we need, we know from the balanced equation that we need the same number of moles of NaOH as HCl. So, we'll need 0.100 moles of NaOH. Now we can go ahead and calculate the necessary volume of NaOH. To find the volume, we'll use the equation V, volume, equals N, the number of moles, divided by the molarity. So, 0.100 moles divided by 0.400 moles per liter equals 0.250 liters, or 250 milliliters. So, there it is. We'd need 250 milliliters of sodium hydroxide to react with 0.500 liters of 0.200 molar hydrochloric acid.
Hey, all this chemistry's fine, but now I think we'd like some complete utter foolishness. Much better.
Section B, dilutions.
Dilutions change the concentration of solutions. When you add a solvent to a solution, it produces a solution of lower concentration. Take the blue dye solution again, for example, right? Now, adding more water dilutes the solution. making the water a lighter blue with a higher percentage of water and a lower percentage of dye.
We can find the new concentration with a simple equation. The molarity times the volume of the original solution equals the molarity times the volume of the diluted solution. You might see the same equation written with C's and D's as the subscripts. It means the same thing as the equation with 1's and 2's as subscripts. The C's stand for concentrated solution, your original solution, and the D's stand for diluted solution.
Suppose we wanted to figure out how much of our original blue dye solution we'd need to mix with water to create a specific amount of a diluted blue dye solution. We'll work a little algebraic magic on our concentration equation so we can find the volume of blue dye solution we'd need to start with. We'll move m sub 1, the molarity of the original concentration, and make it the denominator on the right side of the equation. So the equation now reads, the volume of the first solution equals the molarity of the second solution times the volume of the second solution divided by the molarity of the first solution.
Here's a problem involving volume and concentration using potassium nitrate instead of blue dye. How would you create 250 milliliters of a 0.25 molar potassium nitrate solution, or KNO3, from a stock solution of potassium nitrate that has a concentration of 1 mole per liter?
Again, the volume of the first solution, which is the stock solution, equals the molarity of the second solution times the volume of the second solution divided by the molarity of the first solution.
So V1, the volume of stock solution, equals M2, the 0.250 molar solution, times V2, 0.250 liters, divided by M1, the 1.00 molar solution. That gives us 0.0625 liters, or 62.5 milliliters. So the volume of stock solution we need to create 250 milliliters of 0.250 molar potassium nitrate solution is 62.5 milliliters.
Okay, hi, welcome back to the show. Now, during the break, one of my assistants told me that the professor is going to come back out here in just a moment, and he's just going to do something that's just so wow. Yeah. He's just going to blow our minds, okay? So let's bring him on out again. Professor, come on out and get it on!
Right.
Yeah.
I'm going to make a 0.250 molar solution of potassium nitrate from our concentrated stock solution.
That's why he's the professor.
What I'm going to do is I'm going to take 62.5 milliliters of the stock solution, pour it into our container, and then I'm going to add just enough water to produce 250 milliliters of our desired solution.
Wow! Now, doesn't this look tasty? Drink it up!
So molarity is the number of moles of solute in 1 liter solution. Molarity tells you about the concentration of a solution. You can change the concentration of a solution by diluting it. Adding more solvent to a solution dilutes the solution because you have a higher percentage of solvent and a lower percentage of solute.
Section C, titrations.
You know what acids are. Some sour-tasting foods, like orange juice and vinegar, are weak acids. Strong acids, like hydrochloric acid, can definitely turn you into Swiss cheese if you swallow them. Acids contain positive hydrogen ions, and the more positive hydrogen ions there are, the stronger the acid.
Bases are also known as alkalines. Basic solutions have a lot of negative hydroxide ions. The more negative hydroxide ions, the stronger the base. When an acid's positive hydrogen ions meet a base's negative hydroxide ions, it's like fire meeting water. Poof! The energy gets neutralized. The acid and the base neutralize each other. So, when the right proportion of a base is mixed with an acid, the mixture is neither a base nor an acid.
So, when you mix a basic solution with an acidic solution, the mixture becomes neutral. When the solution becomes neutral, it has reached the equivalence point. Makes sense, right? At the equivalence point, the number of positive hydrogen ions equals the number of negative hydroxide ions, and therefore neutral.
When a base is added to an acid and the solution reaches the equivalence point, the acid's hydrogen ions combine with the base's hydroxide ions, forming water as a product. The reaction's balanced chemical equation will tell you the ratio of starting chemicals you need for the reaction to neutralize or reach the equivalence point. For example, this balanced equation says that 1 mole of sodium hydroxide, NaOH, reacts with 1 mole of hydrochloric acid, HCl, to produce 1 mole of water, H2O, and 1 mole of table salt, or NaCl. We can tell by looking at the equation that we need 1 mole of sodium hydroxide, the base, to react with the 1 mole of hydrochloric acid in order for the reaction to reach the equivalence point and neutralize.
Where are we leading with all this acid-base stuff? Titrations!
No, that's not a titration. A titration is yet another way to determine the concentration of a solution. All you have to do to find a concentration with a titration is add an unknown concentration to a known concentration until the mixture reaches the equivalence point. Then do an easy calculation and you have the concentration. For a demonstration, let's go to...
It's Cooking with Professor Aula!
And once again, folks, Professor Aula.
When we mix a basic solution with an acidic solution, we'll know that we've reached the equivalence point when the mixture becomes neutral. We use dyes known as acid-base indicators to figure out the equivalence point.
Acid-based indicators, ladies and gentlemen. You heard it here first. Okay.
The balanced chemical equation is my recipe. It says right here that we need to mix 1 mole of hydrochloric acid with each mole of sodium hydroxide if our recipe is going to turn out right. So here we have a sodium hydroxide solution of an unknown concentration.
Wow.
Let's see how much we need to neutralize all 25 milliliters of this 0.15 molar hydrochloric acid solution. The acid-base indicator, phenolphthalein, is already in the flask.
Wow.
Now I'll pour in the hydrochloric acid. When I add the sodium hydroxide to the hydrochloric acid, the phenolphthalein will tell us when the the reaction has reached the equivalence point.
Okay.
When it hits the equivalence point, the phenolphthalein will turn pink.
Wow. Oh, now, see, this is amazing, ladies and gentlemen. See, what's happening here is that the solution is actually turning pink, and then it's disappearing. Now, I don't know how much more of this I can take. I mean, this is really exciting. There's the pink again. And now it's not pink anymore. And now it's pink, everybody! Yay, pink! Pink's winning! Now it's not pink anymore, ladies and gentlemen. Hey, now it's pink again! Yeah, pink! More pink! Pink, 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 pink! 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 Now it's not pink anymore, Professor.
The acid-base indicator has turned pink, so the reaction has reached the equivalence point. It's done.
Wow! All right, now I'll take mine on rye. Hold the mayo.
How much sodium hydroxide did you need to neutralize the hydrochloric acid? The burette tells us we used exactly 35 milliliters of sodium hydroxide.
35 milliliters, ladies and gentlemen, yeah.
Yes, and what do you suppose the concentration is of the 35 milliliters of the sodium hydroxide solution?
Well, I don't know. How would we find that out?
Well, let's do a titration calculation.
Yeah, let's do a titration calculation.
Okay, here's the problem. What is the concentration of an unknown NaOH solution if you need 35 milliliters of the NaOH solution to reach the equivalent point of 25 milliliters of a 0.150 molar hydrochloric acid solution?
Jeez, I don't even know where to start with this problem.
Well, think about what it is you're trying to find. Molarity, right? So, Start with the balanced equation that represents the reaction, because it will tell you the proportions of reactants and products in the reaction. According to the equation, NaOH and HCl react in a 1-to-1 ratio. So, we can assume that the number of moles of NaOH will equal the number of moles of HCl. Now, think about the problem. We started with 250 milliliters, or 0.025 liters, of 0.150 molar hydrochloric acid. So, the concentration of this hydrochloric acid is 0.150 molar in 25 milliliters of solution. What concentration would our 0.035 liters of NaOH solution have to be in order for it to react in a 1-to-1 ratio with 0.025 liters of hydrochloric acid? Remember the formula for molarity? M equals the number of moles, N, divided by the number of liters, L. We can fill in the L because we know the volume of NaOH is 35 milliliters, or 0.035 liters. But we need to find N, the number of moles. The equation we'll use to find moles is just a rearrangement of the molarity formula. N, the number of moles, equals capital M, the molarity, times V, the volume in liters.
You're probably thinking, hey, we don't have enough information to figure out how many moles of NaOH we have. Don't worry, we do have enough information. It will just take a few steps to get there. First, check out the balanced equation. It shows NaOH and HCl in equal amounts. That means that the number of moles of NaOH you have will equal the number of moles of HCl. So, find out how many moles of HCl you've got, and you know how many moles of NaOH you've got.
We have enough information to find how many moles of HCl we have, so we can figure that out and apply our result to the NaOH. Convenient, huh? Here's the equation to find moles again. N, the number of moles, equals the molarity, capital M, times the volume in liters. Let's do the math. Our culinary chemists used 0.025 liters of 0.150 molar hydrochloric acid, or HCl. That's 0.150 molar solution times 0.025 liters. That equals 0.00375 moles of HCl. To make it easier to deal with, we'll write this figure using scientific notation. According to scientific notation, 0.00375 moles of HCl is the same as 3.75 times 10 to the negative 3 moles of HCl. Again, since they are equal in the balanced equation, the number of moles of NaOH will equal the number of moles of HCl. So we need 3.75 times 10 to the negative 3 moles of NaOH.
Now we have enough info to find the concentration of the unknown NaOH solution. Use the molarity or concentration formula. Molarity equals the number of moles divided by the volume. In this case, that's 3.75 times 10 to the negative 3 moles divided by the volume, which we've also written using scientific notation. 3.50 times 10 to the negative 2 liters. Cancel it down to 3.75 moles over 3.50 liters times 10 to the negative 1. Our answer is 0.107. That means that 35 milliliters of NaOH solution reacting with 25 milliliters of 0.15 molar solution HCl must have a molar concentration or molarity of 0.107. Wow!
Let's review. Acids have lots of positive hydrogen ions, and bases have lots of negative hydroxide ions. Put acids and bases together, and they neutralize each other. Now you can find the concentration of acids or bases by doing a titration. When you do a titration, you mix a known concentration with an unknown concentration until the mixture reaches its equivalence point. Then, you use the information you have from your known concentration, along with the volume of the unknown concentration needed to make the mixture reach the equivalence point, to calculate the unknown concentration. Cool, huh?
Section D, Limiting Reagents.
A limiting reagent limits the amount of product you can get from your chemical reaction. In most chemical reactions, the reactants are not added in the perfect ratio that's indicated by the balanced equation. So it is likely that one of the reactants will be consumed more quickly than the other. The one that gets used up first is the limiting reagent.
So the limiting reagent in a reaction is the starting chemical that you run out of first. When you run out of it, the reaction stops, and no more of the product or result of the reaction is formed, and chances are you'll have some of your other reagent, the one that's not the limiting reagent, left over. Let's do an example finding the limiting reagent in a reaction.
Let's look at the reaction between magnesium and sulfur that produces magnesium sulfide. When 12.2 grams of magnesium reacts with 24 grams of sulfur, what is the limiting reagent? To find out, we first convert the amounts of our reactants from grams to moles.
All right, we're going to tell you one more time how to find the mass in grams of 1 mole of an element. First, find the element on the periodic table. Here's magnesium.
Move over, Goldie. Listed beneath the Mg in the box is the weight of magnesium in AMUs. It's 24.31. So, we know instantly that the mass of magnesium is 24.31 grams per mole. It's simple. By the way, for our limiting reagent calculation, we use 24.3 grams per mole for magnesium rather than 24.31 because we can only use 3 significant figures. Why can we only use 3 significant figures? Because the terms 12.2 and 24.0 in the problem only have one number to the right of the decimal point. Since we're about to do a multiplication problem, we have to follow the rules for sig figs in multiplication. So, we'll set up the terms in our problem so none of them have more numbers to the right of the decimal place than the number in the problem with the fewest numbers to the right of the decimal place.
Again, we have to find out how many moles we have of sulfur and magnesium. So you need to convert the 12.2 grams of magnesium to moles using the unit factor method. You know that 1 mole of magnesium equals 24.3 grams in weight. So you can put them over each other and multiply by the weight of your total magnesium sample, or 12.2 grams. That's 12.2 grams of magnesium times 1 mole of magnesium divided by the mass in grams of 1 mole of magnesium, which is 24.3 grams. This gives you 0.502 moles.
Now we'll make the same conversion for sulfur. The periodic table tells us that sulfur weighs 32 AMUs, which we know can also be expressed as 32 grams per mole. 24 grams of sulfur times the quantity of 1 mole of sulfur divided by the mass in grams of 1 mole of sulfur, 32 grams, equals 0.75 moles.
The balanced chemical equation we gave you tells you the reactants will react in a 1-to-1 mole ratio. That means that 1 mole of magnesium reacts with 1 mole of sulfur to produce 1 mole of magnesium sulfide.
It's strange to think that you could put 2 moles together and come up with 1 mole, but think about it this way. Say you have 1 dozen vanilla cookies and 1 dozen chocolate cookies, and you want to make 1 dozen zebra sandwich cookies. So, you slop some cream on the chocolate cookies and you stick the vanilla cookies to the chocolate ones. You started out with 1 dozen chocolates and 1 dozen vanillas, but you didn't end up with 2 dozen cookies. No! You ended up with 1 dozen cookies. It works the same way with magnesium and sulfur. 1 mole of magnesium sticks to 1 mole of sulfur to make 1 mole of magnesium sulfide.
1 mole of magnesium will react with 1 mole of sulfur, or 0.502 moles of magnesium will react with 0.502 moles of sulfur, or 0.75 moles of sulfur will react with 0.75 moles of magnesium.
Okay, we get the picture. But the point here is that the limiting reagent in this reaction is magnesium, which, adjusted to 2 sig figs for our subtraction problem, is only 0.50 moles. There is an excess of 0.25 moles of sulfur.